All right, I'm Nicholas Flanders. I'm the co-founder and CEO of Opus 12, and we've developed a profitable solution to carbon emissions. So the vision is to turn something that is currently discarded as a waste product into a multi-billion-dollar opportunity. So just quick company history. There's 3 co-founders. We met at Stanford in grad school. And the way we started the company was at Lawrence Berkeley National Lab in the first cohort of the cyclotron road program. Itasha's from Houston, and most of my family is here as well, so we have strong Texas connections. Since founding in 2016, we've raised over $20 million to date, and we've recently built our first commercial unit. So I'll talk more about what we're actually building. So if you want to think about it at a high level, I usually make the analogy of industrial photosynthesis. So in the same way that a plant takes CO2, water, and energy and turns that into oxygen and useful carbon-based products, our technology takes CO2, water, and electricity and turns that into oxygen and useful carbon-based products. But with our technology, we can tune what you make from the CO2. So many of the things that are made from oil and gas today, we are making from CO2 and water. So specifically, we're focused on commercializing 3 molecules. So these are typical petrochemical building blocks. So carbon monoxide, or syngas, ethylene, and methane. So if you look at the CO2 impact of making these processes from CO2 instead of from fossil fuels, the impact is significant. So take ethylene, for example, which is used to make most of the world's plastics. So to make 1 ton of ethylene, we actually would avoid 5 tons of CO2 emissions. And where that comes from is that we actually use CO2 as a feedstock. So you need 3 tons of CO2 to actually make the ethylene. And then conventional ethylene production is quite energy intensive and releases up to 2 tons of CO2 per ton. So that's where the 5-ton offset comes from. Wide range of applications of this. You can start thinking about many things in your everyday life that could be made from CO2. So if you look at ethylene, it would be the upper in your running shoe. Carbon monoxide can be used to make the foam, which is made out of polyurethane. So you can think about a lot of consumer apparel applications. It can be used to make fuels. So we've been collaborating with Shell for a couple of years, working on CO2 to syngas as a bolt-on to their GTL technology. So you could make a carbon neutral aviation fuel. And the idea is that our technology is a drop-in. So we're not going to go out and replace an entire steam methane reformer or ethylene cracker right away. What we'll do is we'll go to an existing process that uses one of the feedstocks that we produce, so CO or ethylene, and then we'll start by replacing, say, 1 or 5% of the CO or the ethylene. And then that goes into the existing downstream process. We produce it to spec, and then nothing else changes except where the feedstock came from. And then you can have an offtake from a specific customer, say Nike, who says, I want only carbon negative materials. And then over time, we can increase the capacity because what we're building is very modular. So it's a way of dropping in without a huge capital investment requirement, without any operational change, but you end up making carbon negative products using existing downstream technology. So what the technology actually looks like is we have figured out a way to reprogram an existing reactor to do something it's never been able to do before, so namely to split CO2. So what we've created is this new internal component that takes a water electrolyzer and turns it into a CO2 electrolyzer. So our technology actually looks like this, kind of like a chip, and this drops in. We've partnered with the world's largest manufacturer of these water electrolyzers. They're based here in the US. And so our commercial unit looks exactly like theirs from the outside, except it's converting CO2 into new products. So it's a way for us to be capital efficient. We have a very well understood scale-up pathway because these systems have been built at multi-megawatt scale already. So we can get to market quickly, but enable an entirely new application of this technology. So we've recently built our first commercial unit at scale number 1 there. I'll talk about that in a second. And our roadmap is to be at industrial scale. So when I say industrial scale, I mean 1 module that would be converting multiple tons per day of CO2 into any of these products. That'll be in 2021. So just for a sense of scale, reprogramming this technology to split CO2 with our catalyst, it'd be like the CO2 converting power of 37,000 trees but it would be in something that would fit inside of your suitcase. So when we think about customers and partners for this technology, we think about 3 attributes. Do you have CO2 emissions that you want to reduce? Do you have an application for the products that we can make from CO2? And then do you have access to low-cost power? Because that is a critical part. At the end of the day, we're turning electrons into chemicals. So we look at regions like Texas, like Northern Europe, where you have a combination of an industrial base and access to low-cost, low-carbon power for thinking about doing this at scale. Part of the reason we started the company is because we have just hit an inflection point where the cost of renewable power, the cost of carbon capture, and the cost of the electrolyzers that we're building have all fallen combined by about 80 to 90% in the last 10 years. So now you can actually make cost-competitive products without subsidy. And so this is the right time to bring this technology to market. So here's the team, a very happy Opus 12 team. After 3.5 years in the lab with our first commercial system, we'll be testing it at our lab in Berkeley for the next few months and preparing for on-site pilots with partners. So this unit will be making carbon monoxide. So it'll be applications in the industrial gas, chemicals like polyurethane and polycarbonate, and fuel space. So would love to talk to you about potential pilot partnerships and other commercialization ideas that you have. So I look forward to chatting with you over there. I brought the prototype with me, so I'll be on that wall. And in the meantime, if you have any questions right now, happy to take them. Yeah. The question was, what concentration CO2 does the feed need to be? Yeah, so we're in the carbon conversion business, not in the carbon capture business, but you would want to have some level of concentration to make it most economically efficient. So we usually consider the CO2 as an input cost to take account for that. So kind of 90% concentration makes it most economically efficient. So you'd either go to a chemical process that already has emissions of that purity, or you would do some level of capture. So we build that into the economics. Good question. All right, thank you.